Hello everyone, welcome back to the channel PHYT, and today we will be discussing about carbon resistance. What is carbon resistance? Before that, just see this small part of circuit, an embedded circuit which mostly you see in the electronic devices. As you can see here, the small colorful cylindrical components that has been connected within the circuit are the carbon resistors. So these are smaller in shape, made up of cylindrical resistive elements in which embedded wires which act as terminals. These colorful bands are help to determine the value of resistance. Now, as you can see here, a carbon resistance has been placed where four color bands are there. Now, each color band has specific significance. Like the first band shows the first significant digit, the second band shows the second significant digit, the third band acts as a multiplier, and the fourth band acts as tolerance. So, how to remember the series of color code with ease? You can remember it with the help of the phrase BB Roy of Great Britain is very good at work. All those bold capital colorful letters denote the color of the bands in the order as 0, 1, 2, 3, 4 up to 9 till white. And then later on we have the gold, silver and none, that is no band is there, which helps to determine the tolerance value. Now let's try to find the value of resistance for the given example. So as you can see here, this first color is blue, which is 6. So this will be the first digit. Second color is red, which is 2. This will be the second digit. And then the multiplier, that is the black color, that should be 10 then to the power 0 with a plus minus, that will be the tolerance value of 5%. That is, the value can vary within 5%, means it will be 62 ohm with plus minus 5% of the value. So in this way you can obtain the value of resistance, and this is quite helpful in formation of circuit which are quite compact. As a part of exercise you can try to find all this resistance value. Pause the video right here and try to obtain the value. You can find the answer, the value of the resistance which I have asked you to do. If you follow here, a small tick has been used which is used to denote the starting band. Here gold is not used, that is the last band is not used as the first significant digit, because most of the time gold acts as the tolerance value, and hence you can obtain and check all these values that has been calculated here. Now next, now we study with arrangement of resistance. So resistance can be arranged in two simple formats, one in series and another will be in parallel, that we will be studying later. So right now in series connection, no two resistance will have both the common terminal as a part of connection. That is, as you can see here, for this resistance, one terminal is connected with the battery and the other terminal is connected with another resistance. But the second terminal of this resistance is connected with another resistance, not with the first one. And this is what is called no two connections, or the no two terminals will be common for a same resistance. Done. Now current flowing through all the resistance will be same, because the same value of current will be flowing all along all these resistance, and potential along each of these resistors will be different. Now as you can see here, all the markings have been done. I have marked this point as A point, and hence the potential as VA, then VB as this point, this is VC and VD, resistance as R1, R2, R3, and this blue, that is the I current flowing with potential V current. Now this has been obtained with the help of the Ohm's law only. and thus we obtain the potential VA minus VB as the potential drop across the resistance R1. So from the Ohm's law, we obtain this kind of relation as VA minus VB equals to I into R1, VB minus VC as I into R2, that is across second resistance, and VC minus VD equals to I into R3, that is across the third resistance. And we add up, and thus adding up we obtain the potential drop across this end, that is the A point, and across the D point, and thus we obtain VA minus VD as the potential drop across the total resistance or all the resistance that has been connected, and thus we obtain as equals to I into R1 plus R2 plus R3. This brings us with the topic of equivalent resistance. Now what will be an equivalent resistance? As you can see here, equivalent resistance will be such that if I replace this full set of resistance with a single resistance such that all the other conditions, that is the current flowing or the potential drop, all remains same, then I can replace, and that will be the equivalent resistance. And hence you can see here I have written as VA minus VD is equals to I into R equivalent. This R equivalent is the whole replacement of this R1, R2 and R3, and thus we equate it to obtain R equivalent as equals to R1 plus R2 plus R3. So this is the basic formula to obtain the equivalent resistance when you are connecting in series. Series connection is a kind of problem. Problem is, if somehow any one of the resistance gets damaged, then the current will stop flowing. So this makes you understand that this type of resistance arrangement will not be used in our household circuit, and thus we come down to the parallel arrangement of resistance. In this parallel arrangement of resistance, resistance are arranged such that both the terminals of the resistance will be common with any another resistance. Current that will be flowing across all these resistance will be different, and the total value of the current will be same, but the potential across all these resistance, the potential drop across all these resistance are same, and thus we write down the current along each arms will be I1, I2, I3, total value of current as I, and the resistance as R1, R2, R3. And again, simply using that Ohm's law, as we obtain the value of current across each of the arm as I1 equals to V into R1, I2 equals to V into R2, and I3 equals to V into R3. Simply adding up this equation, we obtain as I equals to sum of all the currents through each arm is equals to V by R equivalent. Same that we have studied little moments back. We gonna replace it with an equivalent value of resistance, and thus we obtain the equivalent resistance for the parallel setup as 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3, and this will be the parallel connections equivalent resistance value, and this is the type of connection that is normally used in our household circuit, due to which when any of the appliances running in your home cuts down or power off, all other appliances keeps on running only due to the parallel connection in your household circuit. And now we're going to study about the temperature dependence of resistivity. In our last video, we have been introduced with the term as resistivity, which was the value of resistance that was equal to the resistivity when all the dimensional values were in unit, that is 1, or the relation we obtained for resistivity for a conductor was rho equals to m divided by n e squared tau, where m was the mass of electron, n was the number density within the conductor, e was the charge, and tau, the most important term, was the relaxation time. So in this graph, as you can see here, a simple graph has been plotted, that is resistivity versus time graph for the conductor. This is only for the conductor because we will be doing for other materials also. Now we all know when a conductor is heated, its resistance gonna increase. We have studied in our last video. If you have not followed that, try to get back to the last video. Link will be in the description and or it will be appearing at the top of the screen. Now, as we have already studied that resistance increases due to increase in temperature. But if you deeply look into the fact of resistivity, it will also gonna increase because resistance is directly proportional to resistivity. If you look into the relation of resistivity, you will find that m, that is the mass of electron, n, number density of electron, E is the charge of electron. Those all are constant except the tau, that is the relaxation time. And thus, as tau decreases, rho increases. I know that you will be knowing the reason, but still I will be telling you that as the temperature increases, tau decreases, that is the relaxation time. It is the time between or the average time between two consecutive collisions. So as temperature increases, more of the electrons start colliding among themselves and the atoms start vibrating, and thus relaxation time decreases, and slowly resistivity increases, which makes an increase of the resistance. And thus we obtain the relation for resistivity at any temperature as rho T equals to rho 0, resistivity at a temperature, it is O or 0, then 1 plus alpha T minus T0, where alpha is the temperature coefficient of resistivity. Now if you look into the graph for the variation of rho by T for conductor, you will find that at the lower temperature region, that is around this region, and at the higher temperature region, this is non-linear, but mostly in between the commonly used temperature, not a very high, not very low, the commonly generally used temperature region, that resistivity is linear in nature for the case of conductor. Now at the bottom of the screen, you can see a question, that is to obtain the relationship of alpha with rho. Can you obtain the relationship? Pause the video right here and try to calculate. Or next, I will be calculating this one. Now, you all know that R equals to rho into L by A. This is a very common equation. And thus, RT, resistance at any temperature, can be written as this, and R0, resistance at the temperature T0, it will be written as this. We also know that the equation of alpha can be written as alpha equals to RT minus R0, this one. And thus we obtain, by placing the values right from these equations, as alpha equals to rho t minus rho 0 divided by rho 0 into t, or alpha equals to d rho by dt divided by rho 0. D rho by dt is the variation of resistivity with respect to time, and thus we can define the temperature coefficient of resistivity as the change of resistivity, that this is the change of resistivity per unit resistivity, per unit resistivity, per unit change in temperature. We obtain the definition of coefficient of resistivity. Now we will study resistivity of materials other than metals. So first it will be alloy. For alloy, there is a weak dependence of resistivity with respect to temperature. That is, it will show for a wide range of temperature a linear graph. The variation is very less, and thus we normally use alloy for making any kind of resistance that is mostly used in any circuit or devices. so that its resistance value doesn't changes with respect to temperature. Like if you look into the graph here, you will find the though linear can be said when the graph is like this, but still compared to conductor it has a lesser slope, and thus the linearity is higher than conductor, and mostly alloy is used for the preparation of resistance. And next we come up with semiconductor and insulators. They show an exponential decay graph. This says that as temperature increases, resistivity decreases, both for semiconductor and for insulator. So thus, both as we gonna increase the temperature of the substance, more amount of electron will be allowed to pass, both for semiconductor and insulator. But we know insulator doesn't allow the electron to pass. This is because it depends on the term Eg, and that is the band gap. When the band gap of any material is high, such that when we will be increasing the temperature of electron, it will not get sufficient amount of energy to jump over this gap. So right, for the case of insulator, the electrons cannot jump, but for the case of semiconductor, the gap will be less and the electrons will be able to jump when we will be increasing the temperature. And thus we will be using semiconductor to create more advanced electronic devices that are nowadays used, because we can control the value of resistance and it is quite effective to use. And now, as you can see here, resistance box has appeared. You are quite familiar with this kind of box in your practical lab, because you are not given those carbon resistance to make circuit, but rather you are given with this old kind of resistance, that is this resistance box. So it's generally a multi-valued or maybe a single valued with some denote has been given what will be the value of resistance with some marking. This black top, which is generally plugged out so that the resistance can be added within the circuit. It is generally connected in series with the circuit. But have you ever wondered how this resistance box works? That when we plug it out, the resistance is added, and when we plug it in, the resistance is removed. Let's see. So as you can see here, this is a basic structure of resistance box. Here are the terminals where electrons will be traveling from this minus terminal to positive terminal. So this will be the connection. Now if we pluck out the key, the electrons appears and start moving from the negative terminal to the positive terminal. Now if we plug down the key, now electron will be traveling straight path and reaching from the negative terminal to the positive terminal. And hence we observed that when we plugged out the key, the electron required to travel a longer path compared to when we plugged in. And in this way, due to the longer path travel by the electrons, more amount of resistance is added in the circuit. It's quite simple as that. So up to this, we studied about the various type of resistance that we will be using or seeing in our day-to-day life. Now we will be studying thermal effect of current due to the presence of resistance within the circuit. Now as you can see here, again that a piece of conductor with two terminals and this blue color electron that has been placed now static. Now let me add some potential within it. So this will be the positive terminal and this will be the negative terminal. Now as we give the potential, the electron starts moving in random motion, as you can see here. And due to this random motion, slowly the temperature increases. and with further increase in temperature it gets heated up and further random motion occurs. And in this way, heating of conductor, that is by the flow of electric current, gives us the Joule heating. Now, study about the electrical energy and power. You can see here simply a resistance has been connected with a cell. Current I is flowing through the resistance with VA minus VB as the potential across the resistance. So, we can consider that potential VA will be greater than VB, and thus all the electrons will be traveling with same drift velocity. Why so? We have already done in our last video that we generally consider when electron travels in presence of say an electron or maybe a set of electrons, when travels in presence of potential, all the electrons travel with the same average velocity due to the large number of collisions. They travel with same average velocity, that is the drift velocity. And thus we can consider kinetic energy at point B and point A will be same, but the potential energy will be different depending on the position where the electrons are present. Now we can write current I is I equals to dq by dt, and we can replace dq as the amount of charge that flows within time dt, where dq is equals to n into e. N is the number density and e is the charge. That is that small amount of charge within time dt. And thus we obtain as n equals to I divided by e into dt. Now the loss of potential energy for a single electron when it travels from point B to point A can be written as dw prime is equals to minus of E VB minus and then minus of E VA is equals to E in braces VA minus VB. Then the total loss in potential energy can be written as n into dw prime, that is the number density into the work done for a single electron, and thus we obtain as I into dt Va minus Vb equals to dw, and hence the loss of energy appears in form of heat, and thus heat generated within time t, or the heat energy that is generated within time t, written as W equals to I into V into T, or it can be written as I square R into T. We can write the heat value in terms of calorie because the last one was in joule. So here we can write or convert the term of heat in calorie, dividing it by 4.2, we obtain the equation as 0.24 I square RT, and the unit is in calorie. Now power. Power is rate of doing work, and thus P equals to W by T, hence I square into R, or it can be written as V into I, or equals to V square by R. We obtain this kind of other relations with the help of the relation V equals to I into R, that is the Ohm's law. The SI unit of power will be in watt. Now we will be studying application of thermal effect of current. As you can see here, a circuit has been placed where the key is open and a bulb is placed. Now, as I switch on, the current starts to flow and the bulb starts to glow. How does that happen? You can see here, when the current passes through the tungsten filament, it generates heat energy due to thermal effect of current, and thus with the generation of heat it starts to glow, which provides us with light. So this can be a great example and application of how thermal effect of current is helpful to us. Next you can see few other devices that works on the principle of thermal effect of current. Later on we will be studying about the rating that has been labeled on these electrical devices based on its power consumption. Now we will be studying about power rating of a resistor. So as you can see here, a resistor R has been placed with potential V1 and V2 across its terminal. So this power rating is normally given in all kind of electronic devices, maybe in the form of watt or in the form of current and voltage separately. We just require to product and obtain the power rating in watt. So what is it? That is the maximum power that electronic device can emit without overheating or damaging the device. So now we will be studying about the maximum power theorem. Now what is it? If the output power of a source, that is an EMF source, is maximum when external resistance is equal to internal resistance of the EMF. You are not much aware of the EMF source, irrespective that it is a simple battery, but an EMF source is normally drawn in circuit in a form as, let me draw it out, a small cell with a small value of resistance connected within. So just neglect the bracket. So when this small value of resistance, that is smaller, will be equal to the output resistance, then maximum power delivery can be done by this EMF source. So let's prove this theorem. We know that is I equals to R plus smaller. But how do we do? Let this EMF source within its bracket is connected with an external resistance capital R. This bracket is an imaginary one. Don't just consider it as a part of the circuit. This is just to show that this bracket region will be covering the EMF source and the rest is the external part of the circuit. So thus we can say that this capital R and small r are in series, and thus we obtain the value of current as E, that is the EMF value, divided by R plus, that is capital R plus small r. Now power will be P equals to I square into R, replacing it with I, E divided by R plus R whole square into capital R. We will be obtaining the condition for maximum power theorem only when dP by d capital R is equals to 0, and thus we differentiate it in these following steps that has been written, and we finally obtain that small r equals to capital R. This is the final condition for maximum power generation. So what will be the value of the maximum output power? Replacing smaller with capital R, we obtain at P equals to E square by 4R, and thus we obtain the maximum power by a resistance. So throughout this video, we studied all important topics over resistance, what are the type of resistance that we will be using, and the power generation within resistance. So in our next video, I will be coming up about the EMF sources.